For everyone that's online attending the presentation virtual, my name is George Carey, and we're apologizing for a couple minutes delay, but we're going to get going. I have Will Fisher here with me, and he's kind of monitoring the chat room as well as just make sure that you guys can hear everything we're saying remote, as well as some of the attendees that we have here at FIA in our classroom. And so with that, I'm just going to jump in real quick with just a couple of quick introductions of what the plan is or what the itinerary is for this evening. Just gonna click on it, I think. Get it going. There you go. So myself and Will Fisher both work here at FIA, and we'll be part of the next 4 weeks on talking about this hydronic system design fundamentals. There's a third person down at the bottom there kind of blocked out. I apologize. Dave Salerno will kind of work behind the scenes after the end of each week, after the end of the class of each week. The presentations that we're using, the PowerPoints, will be he'll be loading them up in Dropbox in a PDF format. So everything that we present either online here or sitting here in the classroom, you'll be able to access and hold on to for future reference down the road. So David will be that taking care of that for us each week. It's just giving me a hard time. Just real quickly, we've been doing this, FIA as a company, manufacturer's representative, several different manufacturers. Specifically, I guess the connection tonight would be Bell & Gossett. It's kind of our initial connection with the hydronics industry. Boilers, Lochinvar is a manufacturer that we represent in residential and commercial space for modulating condensing technology. Heat pumps, we handle Panasonic, we handle Gossett. There's a myriad of manufacturers we represent within the hydronics and steam and heat pump alternative energy source market. But historically, Bell & Gossett's been known in the industry across the United States as an educator. They actually have this thing called the Little Red Schoolhouse. It's a facility right outside of Chicago in a town or city called Morton Grove, Illinois. They've been there for forever. And really, they've been doing hydronic classes training in person at this schoolhouse since 1954. So they've been doing it a long time, educating the engineering community, the facilities people, as well as some of our wholesale and distributor personnel. So doing hydronic classes is nothing new. We've been doing it. And it's really, the focus is just some of the principles, not so much product one over the other. It's just what's going on inside a hydronic system. The itinerary, which you guys probably would have seen when you saw the stuff being emailed out to you and you signed up online, but this is the best laid plans, as they say. Hopefully this is what we're going to accomplish over the next 4 weeks. It might bump up one from the other, might just overlap a little bit, as we go, depending upon how quick we get through everything. But the concept is to go through, whether it be tonight, some of the basic hydronic components that are involved with the system, as well as get into the pump curves and system curves and what's that all about. And if we have a little bit of time tonight, we'll also hit on that system size, or that Bell & Gossett system size, or kind of a calculator for hydronics. We'll talk a little bit about that. And then obviously next week, maybe a little bit of a recap, and then we'll just press on. Same with pumps and pump affinity laws, et cetera. Move into our air management, expansion, tank sizing, proper pump location. It's a subject called point of no pressure change. We'll discuss that. And then we'll get into the piping concepts, specifically primary, secondary pumping, and all the different applications that have become very commonplace today in the engineering world. The last week, we classify it as heat transfer. So we'll start, and we'll probably step in. We'll start with heat exchangers and all the different facets of heat exchanger and the applications, how to size, et cetera. We'll show us some of our software that we have at Bell & Gossett office to the engineering community. And then we'll move into the heat pumps and what's going on today with alternative energy and electrification, and how we fit in that space, and how to maybe create some of these hybrid systems where existing hydronic, whether it be chilled water, cooling, or heating with the boiler plant with the new heat pump technology that's becoming very, very commonplace. So that's the plan. Hopefully it proves to be successful over the next 4 weeks. So you guys will be the judge. And with that, let's see if we get to the next presentation. Let's see here. Will, you keep an eye on. I want to get to. Everything's visible. Okay, good. So first subject, we're just going to kind of an overview of what makes up a hydronic system and the various components that you're going to bump up against. It's a very simple drawing. Came from one of our installation manuals, but it's talking about in this case here a boiler plant. So multiple boilers. How is it connected? Connected to a distribution system through primary, secondary T's, closely spaced T's, where we build a manifold, and then we have, in this case here, 4 boilers. Each boiler has its own pump by design from the manufacturer. Because each boiler has its own circulator, its own pump to provide the necessary flow through that particular boiler with pressure drop, et cetera. We just don't want these individual boiler pumps contending with being influenced by, say, a larger existing distribution pump. And conversely, we have a distribution pump that's feeding whatever the case may be. It may be, it could be a campus, a hospital, a college campus, multiple buildings. It could be an apartment complex. It could be whatever it needs to be. We want to make sure that that distribution pump is hydraulically isolated from these individual boiler pumps. So that's a subject that we get into. That's a pretty important design subject. As you get out into the distribution main, very simple, very subtle little drawing, air separators. Hottest point in the system, we're releasing air bubbles from the fluid, from water. We want to have some type of air separating device to prevent air from being a problem. We're going to have an expansion tank. It's a very simple little drawing in this picture here, but expansion tanks play a huge role, very important role. Kind of subtle, sits off to the side. Incredibly important that it's installed correctly, that it's sized properly, and located properly. So we'll get into that. So it's a simple little drawing, but it hits on a lot of different points that we need to cover if you're sitting down, you know, and maybe you've already done some of this and you're just kind of reconfirming some of the principles, or maybe it's somewhat new, and we'll touch on it. Fill valves, pressure reducing valve that's going to bring city water, say, in and fill that hydronic system, make sure it's completely filled with water. What is it? How do we set it? Why is it needed? How does it work hand in hand with its setting, with the pre-charge that's going to take place in that bladder or diaphragm expansion tank you're going to specify, or size and specify. So all these little nuances that all work together. It's a simple little drawing, but we touch this every day, somewhere along the way. A little picture of a mechanical room. Happens to be a couple of Lockavas press boilers, but regardless, X number of million BTU boilers connected to a distribution system through primary, secondary T's. Off to the right here, we have some base mounted pumps. We'll get into that, and some of the trim or the accessories that you're going to see typically associated with that type of pumping. And it's going to be 100% standby. So distribution, primary, and then a backup or a rotation. And that's going to be feeding this hot water out to this particular building or complex. So very simple, but there's a lot going on there that we're going to touch over the next few weeks. Sometimes instead of providing primary, secondary connections and primary, secondary piping, manufacturers say, hey, my boilers it's acceptable to put them in what we would call a variable primary application, where perhaps we're using our distribution pumps to not only provide flow out to our buildings, our terminal units, fan coils, whatever the case may be, but we're also using those circulating pumps or distribution pumps to provide flow through my boiler plant in this case. Now, there's all different little details. We might get into control valves for the boilers that aren't firing. We don't want system flow going through an off boiler, perhaps, and we can talk about that. But this is a common application, and sometimes the argument or the conversation would be, I'm using less pumps. I don't have smaller boiler pumps or secondary pumps for my boilers, and I don't have distribution pumps. I'm using the whole package. Good, bad, or indifferent, doesn't matter. It's an option. It's a design practice. We want to be aware of it and talk about it. This could be an example here, variable primary. They're calling it heating. It could be heating or chilled water. In this case, we're identifying these as boilers. Air separation, expansion tank, pump going through my boiler plant. No primary, secondary, just directly out to my terminal units. These terminal units could be one building, that could be a second building, or it could just be one big building with individual terminal units. Have some type of drive, variable frequency drive attached to my distribution pumps, because as loads change and control valves start to close down, why do I need to keep running that pump as if it's 100% design conditions when loads are changing? I might have some type of DP, differential pressure sensors, remotely located out in the building. And they're sensing a change in flow, change in pressure. They'll feed that back to the drive, which will in turn affect the operation, the speed, the RPMs, which means the flow rate and head that this distribution pump can develop. But more importantly, as it's slowing down its speed, it's slowing down its kW consumption. It's reducing its electrical consumption. And there's the benefit to the building owner or the person that's paying the utility bill. So we'll talk a little bit about that. Going from that type of drawing to perhaps what might look like fairly confusing, but this might be referred to as a primary, secondary, tertiary application, where I might have, in this case, primary or production pumps from my chiller plant. I might have distribution pumps that are secondary pumps that are feeding. In this case, these zones might be buildings, might be dormitories, might be classrooms, might be wings of a hospital. And then within each building, they'll have their tertiary, their third pump, their own pump that's sized specifically for the flow load of the terminal units within that building. So again, that's a design principle that happens quite frequently as well in the industry. So whether it's a simple little variable primary to primary, secondary, tertiary. One last drawing here, I just want to show as an example is this is becoming commonplace now. Maybe air source heat pumps, maybe heat recovery chillers, and then maybe my condensing traditional gas-fired boiler plant. And I might be, acknowledging or trying to participate in that electrification or decarbonization that's taking place in the design world. And so maybe based on loads and outdoor air temperatures, system conditions, I might have the ability to never turn this boiler plant on for certain periods of the year. And I might be using my air source and or my heat recovery chillers. How do I connect all of that technology, all that pumping, and have it all work properly within this system? Well, we'll get into it later on, but primary, secondary T's, this can support boiler plant, air source, heat pumping, the pumps dedicated to the heat recovery chillers, and then there'll be some type of control sequence on how to make this all work. So this is, 5, 6, 7 years ago, this picture wouldn't have been up on the board here. We weren't doing this. We weren't talking about it that much. Now, this is every day, every week, every month. This is happening, across, especially here in the eastern seaboard, whether it be Mass or Connecticut, Rhode Island, New Hampshire, et cetera, Maine. So anyways, these are some of the different design systems. They're very basic drawings up on a board, but this is how they start. And then we get into designing them. So the first component out of hydronic system components, we'll first up, I should say, would be centrifugal pumps. And when you say centrifugal pumps, and you're getting into this hydronic world or engineered world, if you will. We've got all different styles. They all fall under the family of centrifugal. We'll throw up a couple of quick definitions of centrifugal pump, but descriptions: inline pumps, close coupled, split coupled. Inline meaning the volute itself is sitting in line with the piping. There would be piping on either side, and I've got some details we'll show afterwards, but it's technically in line with the piping that the pump is installed. A close coupled motor shaft connected through seals directly to an impeller that's sitting inside the volute, close coupled. A larger, same family, if you will, a vertical inline, but a split coupled. Because as you get into some of these bigger inline pumps, they'll actually come with like a foot base, a foot mounting, so that you can support this pump, this volute part of the pump, because as you get into the higher capacities, say it again. I see what you're saying, Willie. Okay. Stay here is what you're saying. Don't move. I'm just gonna grab my coffee. Got it. So anyways, you were saying, well, split coupled. As you get into some of these larger inline pumps, the horsepower that's required gets very excessive. And at some point, it maybe makes sense to even move away from this technology or this style and move to more of a base mounting, which we'll get into. But the split coupled allows the service technician down the road, the mechanic that's installing these and then needs to go back and service them, to not have to contend with maybe repositioning or moving that motor. They can open up this split coupler, this enclosure, and have access to the impeller, access to the seal. Oops, excuse me. Without having to deal with the motor, whereas this style here, the smaller close coupled, it's a smaller horsepower, so it's not as big of a deal. But if you took that same concept and applied it to this larger capacity, the horsepower that they'd be dealing with would be, unruly. It'd be very difficult. Moving to the right here with this arrow pointing, instead of inline, now I'm getting to what they refer to as a base-mounted end suction pump. And so end suction, all it means is I'm sitting on a base, the inlet is the end of the pump, the end suction, and then I have a top discharge coming up the top here, but base-mounted end suction. As you get into larger capacities, a lot from a service standpoint, from a mechanic working on it, sitting on a floor, easy access, whether it be to the motor, whether it be to the coupler, whether it be to the bearings, whether it be to the seal. It's a easier to service style pump, very common in the industry, with a base that gets grouted. We'll talk a little bit about that later on with some details, but vibration isolation, grouted to the base, to the floor through the base. Very, very common. As you move into some of the larger capacities, you get into these bigger campuses, you're just dealing with bigger loads, bigger flow rates. That's when you get into the double suction, and we'll talk a little bit more detail about that. But what the double suction, whether it be horizontal split over here on the left, or the double suction vertical split pumps. And there's a couple of different orientations, and we'll get into that as well. Real quickly, a definition, centrifugal. So real quickly, a pump itself. A pump is a mechanism used to push a liquid with a specific force to overcome system friction loss and potentially, if it's an open system, any existing difference in elevation. When you talk specifically about a centrifugal pump, it's a mechanism that adds energy in the form of velocity to the flowing liquid. And then the pump produces that velocity through a driver, or in this case, a motor, which obviously consumes energy in the process. So it's kind of a simple, silly little drawing, but it's saying here, if I had this can I filled it with water, and I had these holes at the very bottom, and I had no rotation as that picture on the left. The water would drain out of it at a certain velocity. Just the weight of the water is the motive force. If I add rotation and started spinning it fairly rapidly, and I'm adding velocity, it's centrifugal. I have rotation around a rotor, and I'm adding this energy. That water is going to exit those holes at a much higher velocity. It's a very simple drawing, but that's basically, at the end of the day, that's the operation of an impeller inside the volute of a centrifugal pump. Let's see here. I don't know if I can take that down. I guess that's as low as I can get it. Yeah, that's what I'm. That's why you're here. Thank you very much. There's no Matt. So anyways, just a real simple, again, back to line drawing, but a cutaway of some of the, I guess you'd say, major components or what's going on in the business end, the pump end of a pump. So they got a volute or a volute casing, which would be this right here, this whole outer casting. You've had a suction, a pump suction, and you have a pump discharge on the top. So this would be almost an example of that. Can I go back? Let's see here. Can I go backwards? That's what I just want to, that picture of that impeller, I can't show it up on the screen, can I? Would be very similar to what this would look like if I took that casing off of this pump. That's what I'm showing here. This guy right here. So the impeller has vanes on it, and the vanes are, they're engineered. They're there for a purpose based on flow, pressure differential, all of that, but they're adding velocity to the water, to the liquid as it enters. And the key is that the understanding is, you'll see this expression here, impeller eye. So there's an eye, and that's where the water enters. So in this orientation, that would be that suction, that end suction. That's the entrance. The water's entering into this eye of this impeller. This is the direction. You can see the arrow pointing to rotation. So it's moving in this direction, counterclockwise, I guess we could say. And as it's spinning, those vanes are taking that water and it's adding velocity. And the velocity is at its absolute peak right at the tip of the periphery of the vanes at the edge of the impeller. And then the water is kind of gathered, if you will, in that volute, and then eventually discharges out, if you will. So real quickly, impeller, pumps impeller equipped with vanes. Liquid enters the eye, impeller rotates, adding velocity, causing the centrifugal force to push the liquid out. The force acts on the mass of the liquid, moving it in a circular route away from the center. And again, that velocity is greatest at the impeller's periphery. And most importantly, what's going to happen here is, as it's rotating around in this rotation, it gets to this kind of this moment of, which way do I go? Do I discharge out through the discharge orifice, or do I recirculate, internally and in the at this, what they call the cut water? And from an efficiency standpoint, obviously, we want the majority of that water that impeller is spinning out to the system. I'm using the electricity. I'm spending money on a motor. I want all that water that I've added energy to goes out to the system. And most times, everything size selected, etc. That's exactly what happens. We'll touch on this a little bit later on, because as you get into like a larger commercial pumps, and you get into different capacity ranges, you'll start to see efficiencies and why they change. Some of that has to do with the cut water. How much is recirculating? How much is being discharged out? One expression you'll hear sometimes from the field is, when the vanes or when the impeller is spinning in the proper direction, it's as if the vanes are slapping at the water. They're not scooping, they're slapping, because they're rotating, they're adding velocity. So as that water enters that eye and gets flung along these vanes into that volute, into that casting, and gets directed and discharged out the discharge nozzle. So you get into a couple of different style pumps. The first one, single suction. And all they're referring to is the impeller is known as a single suction impeller. So what they're referring to is all of the water enters into the eye. In this case here, on this top left picture, where the arrows are pointing, that would be the eye to a single suction impeller. Water's entering in to that eye and then is rotating along these veins to its outer edge. You can see the picture on the far right of these, the picture of the tip of the vein. When you look at it, on a sideways view, I guess you could say you could see the shroud which encloses the veins. So that diameter, the width of that shroud, that's going to change depending upon capacity, loads, requirements, high head, low flow, high flow, low, whatever the conditions are. It all plays a part in the engineering and design of the pump. But the point of it all is these pumps down here at the bottom, horizontal inline pumps, horizontal inline, vertical inline, or end suction base mounted. Those are all single suction design pumps. Just a cutaway, looking at the brass impeller, turn it on its side and cut it in half. That's kind of what it looks like. This right-hand side here, that would be considered the eye, where the water would be coming into this as it's rotating, flung along the veins here. In this case, it's the direction of rotation would be this way along these veins, and the water would be discharged off the tips. And then there's just a whole family of inline pumps, whether they be the horizontal inline. In Bell and Gossett's world, it's the Series E60s, but it's a horizontal inline pump with a coupler, I should say. And that coupler is connecting the shaft from the motor to the shaft of the impeller with this coupling. Next family, if you will, same inline pump. It's just called an E90, and it can be mounted in both orientations, vertical and horizontal. And when they say vertical or horizontal, what we're referring to is the orientation of the motor. How does that motor sit? The pump itself can be top to bottom, bottom to top. It can be left to right, right to left. You can change and orient, but you got to be very specific, which way is the motor. In this case here, this E90 is pretty flexible. It can go either way. The 60 always is inline, never vertical. And then the E80s, close coupled, same thing, close coupled up to a certain capacity, vertical top to bottom, bottom to top, and same thing left to right. And some of these as well can be oriented both horizontal or vertical. The split couple is just that larger capacity. If you look at the flows, I mean, it's kind of crazy. I don't know how often we actually see that out in the field. But you go from a close coupled, still pretty substantial flow rate, but all of a sudden you get to this split coupled. It's got some serious capacity, which means some serious horsepower sitting on top of it. And it's why they're going to probably, offer some type of base support for that dilute to support it. But they're showing kind of a cutaway of that split couple where the technician can get access without touching the motor that's up above it to get to that impeller, get to that seal, etc. End suction, just like we talked about, these two pumps are both end suction. One's a close coupled with a little foot base right here. Oops, excuse me. And then obviously the one on the left here is with a coupling with a bearing assembly coupler guard and a motor sitting on a frame, sitting on a base. Both are what you refer to as that end suction. From the field, here's a couple of pictures of one of those, or two of those pumps, if you will, with a bunch of the accessories that we'll touch on real quickly. But that's pretty common. That's a pretty standard type of pump you're going to see out in the field, this base mounted end suction. The accessories. So on the bottom left, that's kind of circled right here in the drawing or the slide, they're referring to a suction diffuser. So we'll just explain real quickly what that's all about. There's different styles, if you will, flanged connections. Some of the smaller ones might even be threaded, or maybe some type of Victaulic connection, depending upon the application. They're just showing off to the right here a newer design. But I just want you to pay attention to this little, they call them veins, that's sitting inside that volute. That's very important. That's the whole kind of secret, if you will, of the magic behind what we refer to as a suction diffuser. And so real quickly, why? Why suction diffuser? Well, when you're changing, in this case here, they're saying a plane change. So maybe I'm coming down vertically, and now I'm going to enter into that end suction. I'm going to change my direction. And from that elbow, when I make that change, there's different velocity taking place. The flow rate, as soon as you make that plane change, isn't equal, if you will. What they refer to maybe as a non-uniform flow pattern. And if that was to hit the impeller, that would load the impeller unevenly. And if you think about the impeller, what's behind it is the seal, a shaft, a bearing assembly, and you're really wreaking havoc with the life, the expectancy, the function of that pump shaft steel. And the industry's known that for years. And the way they addressed it is they said, hey, I want a straight run of end suction pipe diameter, a straight run of pipe to straighten out that plane change. And you say, okay, well, that's the way they solved it. You start getting into larger applications, the diameter of the pipe is pretty substantial, which means the 5 pipe diameters can be from a floor space, taking up mechanical floor space room. So X number of years ago, some of the engineers at Bell and Gossett came up with this suction diffuser. And basically what it did is it has this baffle or these straightening veins internally inside this body, as well as like an operating strainer, which they refer to as an orifice cylinder. And then they'll have also in that suction diffuser, is they call it a startup strainer. And that startup strainer is just to be there for, like they're saying here on the screen, a couple of days. Turn the system on, you commission it, you're running it. But on the construction site, there's sediment, there's stuff in the system. We want to, use this startup strainer to maybe catch as much stuff as we can before it gets to the seals of the pump and damages, or even the impeller. So the suction diffuser, let me back up here. What it's doing is it's taking these through these veins right here in that small little footprint, is it's allowing that plane change to evenly load that impeller, so that and that vein will then act as if you had provided that straight run of pipe. So it's a space saver. It's been around for a long time. Any type of end suction, almost always you're going to see that specified as part of the accessories on a base mounted pump. Whoops. Other accessory on the discharge side, they're going to call it a triple duty valve. Triple duty, 3 functions. And I'm trying to explain at the top, but it can act like a balance valve, throttling valve, balancing, kind of bringing that pump in line if need be, if it's oversized. It acts like a check or spring-loaded soft-seated check. And then it can also act like a service valve. So you can close it right down and isolate the system side from that pump. And then you're going to have a valve back here that's going to close, a butterfly valve of some sort to isolate the pump from the system. It's going to be a soft-seated check to prevent reverse flow, especially if you had 2 pumps in parallel. You don't want one pump running backwards through the off pump. The check will check that. And then, it can also act as a balancing device. And here's just a little bit of a checklist. Service valve, check valve, a throttling, a balance valve, possibly also a flow meter. And then depending upon the orientation, some of them are straight through, others could be almost used as, right here, they're showing as an elbow. When you're going to select them, when you select them and you're looking at that suction diffuser, and in this case here, the triple duty, you're looking for full flow. What's the design flow rate that you're going to be using with this pump and this system? Make sure that this triple duty valve is sized for it. Make sure when you're selecting it that it has a minimum of 3 feet of head loss. On the high side, the maximum, ideally don't select it for higher than around 25 feet. But we want to have some pressure drop so that we can actually use it for accurate or fairly accurate flow determination. So you got the pump, you got the suction diffuser, and on the discharge side, we're going to have this triple duty valve. And that's just kind of a cutaway of what it looks like on the inside with that spring-loaded, soft-seated check. And then the last thing, just for a couple of accessories, is going to be these flex connectors. And the flex connectors, typically it might be just last minute alignment, taking that system piping that's coming back and align it to, in this case here, maybe to the suction diffuser, and then on this side the discharge tying in. And there was a screen back here that talked about typically from the discharge of that pump before we get to that triple duty valve, they're looking for a minimum of around 3 pipe diameters. They could use that flex pipe to fill that gap, as well as, again, alignment, just lining up from the discharge of the pump to the triple duty valve. Pretty common stuff. A couple of details that most of the engineering firms have developed over time, whether you're dealing with the end suction pump over here on the left, and some of the details that you'll use or that the engineering firm has established to give to the trade. Inline pumps, you're saying, geez, there's 3 different details. Well, it really gets into how big's the pump, how big's the horsepower, what's the flow rate, because it will impact how are we supporting, because we're never really attaching to the pump itself, but we want to support the piping on either side, suction and discharge. And then how rugged or how robust that support is as the horsepower gets larger. In this case here, they're talking, let's see here, up to over 3 horse and maybe somewhere around 10 horsepower. And then as you get over that 10 horse, that's when you're going to kind of get into that split coupled vertical inline. Well, they'll actually have a spool piece and a base to support, because you're dealing with some serious substantial weight. And then foot supports on either on the piping on the discharge side, as well as on, in this case here, they're actually using that suction diffuser on the suction side of that large capacity inline. So there's options. Just a quick comment. We're talking inline pumps, vertical, horizontal, base mounted, all of that. There are smaller, inline cartridge style pumps. Typically, you're going to find them mostly residential. You might find them in a small, light commercial space. Same concept. They're just obviously a lot more compact, expense-wise, relative to what we just discussed. They're going to be a little, sometimes considerably less expensive. One other technology, we'll spend a little more time next week talking about it, but ECM circulators have made their way over to the United States the last 5-6 years, maybe a little bit more. And so there's a couple of quick screenshots of, we'll call it like a residential and then perhaps a light commercial ECM offering from Bell & Gossett, but regardless of manufacturer, ECM technology is here. The utilities have embraced it. They've offered various incentive rebates over the years to get this technology out into the field. ECM, very easy to say, electronically commutated magnetic motor is what it stands for, which is why we stay with ECM. It's a lot easier to pronounce. But what they're referring to is they install magnets on the rotor, which is part of creating that magnetic field. Another thing that's very different, and sometimes you'll hear the expression when you talk ECM, is people might say, hey, that's a smart pump. You get smart pump technology. And what they're referring to is in the operation of these pumps, most times when you use an ECM, you're going to have a microprocessor. There's a printed circuit board on board the drive in that pump. And with that comes some software and comes some intelligence and comes some flexibility on how you want to use the circulator. And what they're trying to say here is real quickly, again, like I said, next week we'll do a little deeper dive, but power is pulsed on and off electronically to create the magnetic field in the stator. The magnets on the rotor react to that magnetic field, opposites attract, north, south, etc. Creates rotation. The faster it's electronically pulsed on and off, the faster the rotation, and then the slower the pulsing, the slower the rotation. So you're impacting flow rate, head, and most importantly, kW consumption. We'll take a deeper dive. But that technology is here. It's not the panacea, it doesn't solve all the world's problems, but it has a very nice spot within the industry. And where it does fit, it works very, very well. So just wanted you to be aware of that. This last section of centrifugal pumps I just want to touch on is referred to as the double suction centrifugal pumps. And just as a description, single suction impellers, these are double suction impellers. And as this drawing is trying to show here, is we'll actually have water enter both sides. There are two eyes to this double suction impeller. So it enters to the right-hand side here, and it enters into the left-hand side. And the reason for that is you're getting into really higher flow rates, higher capacity pumps. And if you were just taking that traditional end suction pump and putting all of that flow, all of that force on that bearings, shaft, seals, it can get pretty excessive. With this double suction, they almost cancel each other out. Instead of hitting it with one, you're actually evening it out so that as the flow comes in equally, and that's what they'll do, is take whatever that flow rate is and equally split it so that they enter equally into each side of that eye to evenly load and take away that load, that thrust that's taking place on the less expensive, more appropriate when the loads are low, but when the flow rates get higher, it makes more sense to move in this double suction arena. And so the pumps down below that support that or use this technology are some of our vertical, split case inlines, horizontal side inlet. So different, larger, much larger, typically all base mounted, but they are split coupled, if you will. So horizontal and split vertical double suction. It's a little hard to see here, but what's going on here is this is our suction in this orientation. And the reason we know that is if you look at the shape of this volute, we'll call it a volute right here. It's like a V. It's pretty obvious. It's a V or an upside down V, I guess I should say. And on the inside, there is a splitter. There's actual casting, and it's taking that water and it's forcing it to split and then enter into that impeller on both sides. So this splitter here takes that suction and equally splits cut that flow in half so that it enters on either side of that impeller. So that's your horizontal or vertical split double suction pump. And there's all different configurations. They call it nozzle configurations. Obviously not that important tonight, but as you get into down the road in your career and you're selecting, what's my orientation? What's my rotation? Right hand, left hand? Am I doing both vertical suction and discharge? Which this is probably the most preferred style, this guy here, left or right. Only because if you think about it from a floor space standpoint in that mechanical room, your piping is up high, coming down, dropping right into that casing. These other two down here on the in the middle and on the left, which sometimes they might have to because of the orientation. This VSCS, this side inlet, this side horizontal inlet, it might be the application more like a cooling tower, and the piping is down low. And we're going to enter right into that side. That'd be an application for that VSCS. And then other times, just from maybe an existing installation, I might have this, what they call a horizontal split case. And it's horizontal suction, horizontal discharge. So you have these different configurations. You just want to be aware. But the whole family is double suction. And you're getting into much higher flow rates. The load is too great to put it on that one end. Evenly load the impeller and the shaft and the seals. This is kind of a picture of what you're not supposed to do. And it's just the don't part of it is how they took this elbow and just connected it right to the suction of the pump. And it's creating this greater flow, if you will, one side versus the other. What I just like is this part right here. This is the splitter. This is the casting inside that body that you can't see from the outside. And when it's done right, as that flow comes in, it will split evenly to one side as well as split evenly to the other. So you're evenly loading that impeller. And again, a lot of the engineering firms over the years have come up with their own version of pump details for these various orientations, vertical split, side inlet split, or in this case here, a horizontal split. Sometimes a question will come up, hey, when do I make that decision? When do I go from one to the other? When do I go from end suction, single suction, or excuse me, end suction, single suction impeller to a split case double? And it's not written in stone, but kind of a rule of thumb that the industry's accepted. It's typically flow rates as you start moving up over that 1,500, 2,000 gallon a minute, you're probably going to move into this split case double suction versus the end suction. Can you see selections with this style pump? Absolutely. But the wear and tear that pump is going to go through longevity wise and the service that's going to be required to keep that pump up and running is going to be different than making, unfortunately, well, not unfortunately, but just the reality, a more expensive cost up front, but a much more robust design to operate with that higher flow rate and not have these service issues is that split case double suction. So again, like I said to you at the beginning, these will all be available on PDFs, but this is kind of a nice little single page or single slide, but a chart saying, hey, industry standards, rule of thumb, when to go, when to move from one to the other. It's a useful sheet. Again, nothing written in stone, but very useful. Moving away from pumps for a second, getting into what we'd call air separators, another component that's very important in the hydronic system, both heating and cooling, but especially heating, but it has its place in the chilled water world as well. So just a statement out of an older ASHRAE systems and equipment handbook. But if air and other gases are not eliminated from the flow circuit, they may cause binding and terminal heat transfer elements, so fan coils or what have you. Corrosion, certainly noise, it'll create a noise factor that would be objectionable. You're unloading or deloading on an impeller that's spinning at a certain RPM with a certain load, and all of a sudden a volume of air comes in. It's going to reduce pump capacity as well as hydraulic stability. We'll explain that a little bit later on, but I don't want air floating throughout the system. It can wreak havoc with the operation of the pump as well as all these other previous elements that can take place or maladies. So where's the air come from? Well, it's just a very, very simple picture. It's actually out of one of the manuals that are either online or the people here in the classroom have in their engineering binder. Just simple tap water. You fill in the system, H2O. There's oxygen. And oxygen can stay in solution based on pressure and temperature. And as you change that, as you heat the water or lower the pressure, it can't hold as much air. Air can't stay soluble. So it comes out in bubble form. So just simply filling a system and then heating it, if it's especially in a boiler plant, you're going to have air coming out. So we want to make sure that air doesn't do this, become a problem. So we're going to have some type of air separator. So what this is kind of the simple screen here is just saying, hey, there's different technologies. Velocity is a method that they use to separate air from water. Coalescing medium is another method. And then centrifugal acceleration is the third. And these are pretty standard accepted technologies that are used. And then you'll see small or large. And then as you get into residential sizes, or you get into the commercial with these roll air troll or these larger coalescing air separators. So the first guy up, based on, like it said back here, based on velocity, it's a simple little air scoop or an air separator is the term you'll see out in the industry. And the way it works is the diameter of the piping, right? There's a certain velocity, feet per second. How fast does that water move? And there's an engineering standard, and it's very accepted, typically 4.5, maybe 5 feet per second. And so this simple little device is actually engineered diameter-wise relative to the pipe size it's attached to, so that flow goes from 4.5, 5 feet per second to a half a foot, 6 inches per second, I should say. So it's just a wide spot in the river. So it's a certain flow rate, and all of a sudden it separates. It slows down, and it gives the chance for the bubbles, the air bubbles, to separate that have been released from the heat source, that heat exchanger, that boiler or boiler plant. So it's a very simple device, but it does work. It's more common residentially than commercial, but just be aware of this technology. Velocity is the method they use to separate the air from the water. The next one up, very popular residential, light commercial, would be this coalescing. And what they're referring to is the coalescing medium allows these smaller bubbles to combine. They kind of gather. And what happens is the velocity in that area and the surface area of these fingers, these stainless steel little fingers that allow these smaller bubbles to gather, when enough of them gather together, it becomes a larger, more buoyant bubble that will then release and vent out through the system, through the vent that's located on the top of this device. So it's surface area. It's given the flow, as the flow's coming through with these bubbles, it's given these bubbles surface area to grab onto. Commercially, it would look something like this. And again, ASME rated, very effective, perhaps on the pricier side of technology, but very effective at separating air from the pumped flow. So that would just be the commercial version of what we'd call a lighter commercial or residential, but air separator coalescing. The last, excuse me, that's just a spec sheet, if you will. Pretty impressive in terms of what you're looking at for flow rates as you get into some of these larger, commercial settings. In what size? 2-inch all the way up to 24-inch. So I haven't seen a 24-inch live in person. Will, I don't know if you've bumped up against it, but I'm imagining it's like the size of a refrigerator or somewhere in that range. It's quite impressive. The last technology that we would use in terms of air separation as separator is centrifugal action. This particular picture would be a picture of a roll air troll, is the term that Bell and Gossett would introduce. And they make this statement up here. They call them a tangential air separator. And so the inlet and the outlet are on the same side of that round vessel, if you will. So I'm looking at it straight on. If I had a bird's eye view looking at it or a plan view looking down, the inlet and the outlet are on the same side, but they're at different heights. So as that water's being pumped through, the flow rate's coming through, it creates this, and this is kind of a computational drawing, if you will, but this circular. And what they're saying here is I've got air and water coming together, going through this device, and it's spinning. The air is lighter, the water's heavier. The water's going to get thrown to the outer edges of this shell. The lighter air collects in the interior, and there is actually they'll have like a collector tube, they call it a stainless steel air collector tube internally here. And so the lighter air gathers in the center, and the heavier water that's separating from the air discharges out the discharge nozzle, air free. Now I'm going into a suction of a pump, perfect. Now I'm going up to the building, air free, perfect. That's what I'm trying to achieve here. So this technology, very effective, very common in a commercial space. So either I'm doing coalescing, one of these guys in a commercial setting, or I'm going to go with this roll air troll, this centrifugal action as my air separator. Both of them are effective. Lower flows acts as a velocity reducing. As you get into your design flows, your higher flows, it's that centrifugal action that takes over to allow the air to separate and gather in the center of this shell, if you will, this collect, and attached to this stainless steel collector. Then we've got some spec sheets. They've got some submittals where they talk about the amount of air that passes per amount of air that's separated per pass. It's quite effective. The last device that's made its way onto that commercial setting is referred to as either a low loss header or a primary secondary header. We'll see this again in week 3 when we talk a little bit about primary secondary pumping and piping. But this device, it kind of performs a few different functions. It starts off being called primary secondary header or a PSH. And what they're saying here is this is such a low velocity device that I can hydraulically separate, say, my boiler plant from my distribution plant or my distribution system. And because of that low velocity, I can act like an air separator as well. And so they'll do that. And these devices, whether it be a small little 2 or 3 inch or come up to a larger, I think it's up to 6 or 8 inch, they'll come with a high capacity vent. So as this pumped flow coming from my boiler plant with hot water with air bubbles in it enters this area here, the velocity is such that the air is allowed to separate and vent out. And then the other function that some of the guys in the industry will take advantage of is if I'm in a mechanical room where maybe it's not a brand new building, but it's a retrofit, it's a renovation. So I have existing piping and radiation out of the building, but I've cleaned up the mechanical room. I might have some sediment coming back from the system. What I can do is I can use this device, again, because of the low velocity, as a dirt separator. So I can be my primary, secondary connections, I can be my air elimination, and it can be my dirt separator. And then what happens is they'll add this drain, this valve at the bottom, and use it as a blow off. So they'll blow off any of that sediment that might collect at the bottom of that air, of that low loss header or that primary, secondary header. Just a real quick cutaway, the way it works, again, back to what pipe diameter and then what's the diameter of the shell. And it's very engineered, it's very specific. So that the 4.5 feet per second velocity as it enters this diameter, it drops it to just basically less than 1/2 foot per second. But it's a low pressure drop, works well for primary, secondary connections, works well to separate air bubbles from the pumped flow, as well as potentially a place to gather dirt separation and then blow it down through your blowdown valve. One last statement or point of reference, if you will, question comes up, hey, where do I put these? Where do I put an air separator? What's the most logical place? Well, the hotter the water, the less air it can hold. The cooler, the more it can hold. The lower the pressure of the water, the less air it can hold. The higher the pressure, more air is in solution. So therefore, when possible, select a point which will have both the highest temperature and the lowest pressure. And then when it's kind of not possible, ideally, highest temperature is going to have the most influence on releasing air out of solution. So again, that's why typically we're going to find air separators at the outlet of a heat exchanger, the outlet of a boiler or boilers. That's where I want. Now, when we get into pump location and how pump pressure differential can influence system pressure, if I'm on a suction of that pump, I haven't seen the pump's pressure, I'm at a lower pressure than what the system's going to see when that pump's adding its pressure differential. So at the hottest point, ideally at the lowest pressure if possible. Next component, if you will, that we're going to come up against, compression tanks, expansion tanks. They have a bunch of different terms, if you will. Again, line drawings, but what we're showing here is 3 different technologies. The old style, if you will, a steel, a standard tank, they might call it, or a standard compression tank. I'm going to show you guys what this is and make you aware of it. You're probably never in your career ever going to specify something like this. It's going to be down here, either a diaphragm style or a bladder. But every now and then out in the field, you might bump up against, you just want to education-wise, just be aware of what that technology was. The main difference right here, there is no bladder. There was no bladder. Butyl diaphragm hadn't been invented, to be quite honest with you, years ago when they started first using this closed compression tank. So the air and the water saw each other. They touched. There was no separation. And they engineered the system and it worked, but it was fairly finicky. So once the diaphragm bladder, question or stretching, came along, this technology took over. Bladder diaphragm is what you're going to see, what you're going to specify all the time. To take a quick trip in the Wayback Machine, hydronic systems, when they first came out here, especially here in the Boston area and the East Coast, gravity hot water. So that truly was what they would refer to as an expansion tank. It wasn't closed. It was open to the atmosphere. And its purpose was, as that coal-fired boiler down in the basement truly heated the water and the water expanded, it had a place to expand into without building pressure and either causing a bomb or a relief valve to do its job and relieve pressure. Typically, it wasn't uncommon to have these old tanks up in the rafters, up in an attic, perhaps highest point in the system, with a pipe, an overflow pipe, and a vent, literally penetrating the building, the structure. You know, long ago, every now and then I'm out in the field all the time, but every now and then I bump up against an old McMansion, and it might have the remnants of one of these tanks sitting up in the rafters. And it's, has since, been disconnected and the system's changed, but that was kind of the beginning. And that's why they call them expansion tanks, because they truly expanded. When I have this screen here and it says compression, it's a play on words. Everyone accepts the word expansion, so don't be afraid to use expansion tanks in your career moving forward. It's perfectly fine. But the difference that they would kind of technically argue or discuss would be whether it's a diaphragm or a bladder or this old steel standard, you are compressing air. Expansion tank, there was no compressing. It vented out of the system and the water just expanded into the tank. Once they sealed it, and that's what these compression, once you sealed it and you weren't open to the atmosphere anymore, it was closed. Technically, you were compressing. And then as the water cooled, that spring would expand, that gas would expand. So it was compressing constantly, either squeezing or expanding. So, but again, the industry's moved on and said, look, they're all expansion tanks. Fine. Why do we need them? What's the purpose? We're going to do a much deeper dive next week. We'll get into air management, or the third week, I guess it is. But the role of a tank is this: maintain pressure within an acceptable band. I got to fill the system. I don't want my relief valves active. I want it closed. I don't want water dumping on the floor every time my boiler plant fires. So I have a responsibility of this tank to keep the system pressure within a high and a low. Establish a minimum cold fill. We'll talk more about that. NPSHA, we'll get into NPSH, net positive suction head, what that means later on. Thermal expansion, everyone kind of grabs that. Yeah, as we heat the water, it expands. I gotta have a place to have that expansion take place. May act as an air separator. We'll talk about that. And as we get into the point of no pressure change, pump location serves as the pressure reference for the system. So even though we say, I need to specify, I need to put in an expansion tank and it sits off to the side, it does perform a lot of functions. When it's working fine, you don't even think about it. It's when it's not working that it becomes a conversation piece. So, picture speaks 1,000 words here. 2,000 gallons of water, fill the system at 40 degrees street temperature, say. I heat the water to 180 and I have an additional 56 gallons of volumetric expansion. Water's not compressible. Where do I put this 56 gallons? And don't create either one, a bomb, or two, a relief valve that exceeds that expansion and opens up to protect the equipment and dumps all the water on the floor. That's why we have expansion tanks, diaphragm, bladder, whatever, is to accept that expanded volume, let the pressure rise, but never get to the point where it's critical. It's below that threshold. So that's like I said, picture speaks 1,000 words. This is the reason for expansion tanks, or one of the big reasons. Two real quick typical piping or applications, if you will. This is that old system. And when it came out years and years ago, they called it air control. And what you'll notice, one, you get that old style standard tank compression. There are no vents. They did not use automatic vents in an air control system. Because the whole idea is the air and the water, because they were touching each other in this tank, as the system heated, air came out of solution. What I would do is I would put it through this air separating, here it is, air separating device, and I'd take any of that air and I'd direct it, I'd control it, send it to that tank. Now the boiler shuts down, the system's satisfied, everything starts to cool. Well, as it cools, water can now start to absorb the air. So this air, this nitrogen is moving in and out of solution as the system heated or cooled. So the whole idea was, because the tank relied on this air as the spring, the cushion, I didn't want to get rid of it. If I vented it, then I'd lose my cushion. And what would happen is the system pressure would drop. And then right over here, you've got this thing called a pressure reducing valve. And he would sense that drop in pressure and he'd add more water. Well, the only place the water would go would be in this tank. So all of a sudden, this air cushion water you decided to lose the air cushion. Now all of a sudden, you just got a tank full of water. Boiler turns on, no place to go. Relief valve dumps. Facilities people come over. They got to mop up the water. They're all frustrated or whatever. So this system, years ago, they never used air vents. The only reason I show this one picture here is I get a kick out of it. I had an engineer who specified this technology, which is brand new stainless steel modulating condensing boilers in a mechanical space, which is fine. It's normal. That's what we do every day. But he was kind of an older school engineer, and he specified this steel compression tank with an air troll fitting and one of those inline air separators, because that's kind of what he was schooled on as a younger man in the industry years ago. So he takes out the old technology, puts in this high efficiency condensing boiler plant, but he put in these compression tanks, which it's kind of like an oxymoron. You're going with high efficiency, new technology, but what he was educated and schooled on and what he felt comfortable with was the old air control, which is this system. Very rare. Never going to see that. You're very, very infrequent. Did it? Oh yeah. Yeah. The guys putting it in had a lot of questions because they just weren't schooled on it. They hadn't seen it. One of the first questions would be, what in hell is that? And it's part of the system. It's called an air troll fitting. And it's a fitting that gets inside the tank, because the tank had to have a certain ratio. A better picture would be here. When you filled that system and it was cold, there was about 55% water, 45% air. Well, how could you establish that? So what they would do is they would use this air troll tank fitting that had a tube inside here. And it was a tube within a tube. And as you filled the system, you had the vent at the bottom open. And as the water's coming in, it's displacing the air out this vent. When water would suddenly start kind of dribbling out the bottom vent here, the guy would close it. And now we had the right ratio of air to water in the tank. These guys thought they, had an epiphany. You're like, what? We've never done that, something like that. So to your point, it did work, but there was a lot of hand holding. But today, it's this. This is what you guys designed. This is what you're going to see. This is what your offices are all seeing, what you're going to see on the field. They call it air elimination as a simple statement. Any air that gets released from that water that gets heated, get rid of it. I don't need it. I don't need to control it. I want to get rid of it. I want to eliminate it. Because down here is in this case, a bladder style expansion tank or compression tank that has a charge of air in the shell. In this case, it's in the shell of this bladder tank. And it's not going anywhere. It's always going to be there. As long as there's no leaks and all of that, the components are all fine. So any air that I catch, look what I do. The manufacturer provides this high capacity commercial grade vent. Get rid of it. Don't worry about it. Just get rid of it. And what's really good about this orientation here is this is the discharge coming out of that air separator right into my suction diffuser, right into the eye of the impeller, right into my pump. So I'm providing nice air-free water into the pump. Perfect. It's exactly what you're trying to do when you're sitting there designing that system. It all comes together. I got air separation in between the air separator and the pump. Here's my compression. Here's my expansion tank. These are just little piping details. We'll get into a little bit later on, like I said, in the following weeks on how to install it. But that's a very good installation of an air elimination. And there's just two styles, bladder or diaphragm, two different types. And it's usually, they achieve the same purpose. One has to do with the smaller systems. The diaphragm is a little less expensive, if you will, in the expansion tank world. So for the smaller hydronic systems, we're going to use diaphragm. And then at some point, as you get into software and you're doing your software selection, which we'll go through an exercise later on in a couple of weeks, at some point, the diaphragm tank doesn't make sense, and I'm going to this bladder style. And it's designed for those bigger systems with more water, more expansion. They come pre-charged. Again, we'll spend more time on this, but the pre-charge of a diaphragm or a bladder has to match the fill pressure requirements of the system you're attaching it to. We'll get into more details, but it's a very important piece of information. What I like about this picture, it's very, very simple. It's almost like a smaller residential tank. But what happens is when these tanks get installed and the system is off, it's not hot, it's cold, you're just putting the system together, there's not supposed to be any water in the tanks, just air. Whereas that old steel compression tank that was up hanging up, that had 55% water. It was a much bigger tank. There was a lot more details. It was very challenging or finicky. These guys are much more less finicky, very flexible, very easy to install. We just need to understand. So when I install it into a system, that's why I keep saying that pre-charge in that tank has to match whatever my fill valve, my pressure reducing valve is set for, so that they work together. So that when I attach it, it looks like that. There is no water in those tanks until such time that you turn the boiler plant on and you heat the water. Now, as it expands, again, water is not compressible. The only place I can go is where I have this body of air. Air is a gas. Gases are compressible. That's where it will go. It'll squeeze that cushion. A couple of cutaways, just kind of cool, just to see what the innards look like, whether it be that full acceptance bladder on the left or this diaphragm, partial acceptance, but with that diaphragm fully extended, if you will. Next device that we want to talk about is a PRV, a pressure reducing valve. A fill valve is another term you'll hear out in the industry, but basically their job is to take city water, city pressure, and knock it down, reduce it to what the particular system it's being attached to needs for water, fill pressure to fill that system. It's a hydronic system. We need to have water everywhere. And most importantly, all the way to the high point. So how do you set them? It's a function of the static height of the system. In this case, it's a simple little drawing, a two-story house. But whatever it takes in feet to go from wherever it's located, typically down in the mechanical room with the boiler plant, et cetera, to the highest piece of radiation or piping. It's that simple. It's that straightforward. So again, a real simple, to calculate required fill, divide the number of feet from the basement, if that's where the fill valve is, to your highest piping. What is it in feet? Divide it by 2.31. We could talk a little bit later on where that number comes from, but divide it by 2.31, and that becomes your fill pressure. And then this little statement here is very important to recognize. To whatever that number is, to this number, add 4 pounds. Because if I took that math and divided it by 2.31 and come up with a number, if I set that fill valve for that number exact, what's the pressure up here at the high point? It might be 0. So I got the water up there under no pressure. I don't want that. I want positive pressure at the high point. If I have any vents on the high point, I want vents to vent. Vents are vent into the atmosphere. That's 0 pounds gauge. If I have 0 pounds on the system side, 0 pounds on the outlet, there's no motive force. I'm not doing anything. So industry standard says, hey, whatever it takes to get there, divide it by 2.31, and then to that number, add 4 to 5 pounds. Now I know at the high point, I'm pressurized all the way up. Ideal location, usually as close to your expansion tank, your diaphragm, your, in this case, bladder. Doesn't have to be right on it, but in this case here, it's right close to my air separation, my cold water line that's coming in with my fill valve. So it's all within, very close proximity of each other. That's a pretty good location. Because the whole thing is, I want that fill valve to only respond to one thing. What's truly happening to the system's fill pressure? Not pressure changes because the boiler came on, not pressure changes because a pump turned on and either dropped pressure or added pressure. I truly want them to just respond to the actual system conditions. Last piece of, last component, our relief valve. Kind of sits off to the side on top of a heat exchanger, on top of a water heater, on top of a boiler or boilers. Hopefully it's never active. Hopefully it's never needed, but it's there for a reason. It's engineered in accordance with Section 4 of the ASME Boiler and Pressure Code, certified by National Board of Boiler and Pressure Vessel Inspectors. It's a pretty important device, very important device. It has two capacities that it needs to meet, two settings, if you will, when they're selected. So one is the pressure setting. It has to match. In this case, they're making the statement a boiler. It could be a boiler, could be whatever that appliance is, could be a heat exchanger, but whatever that heat source's maximum rated operating pressure is. So that's one. That's one number that it needs to meet. The other part, which is just as important, is the relief capacity, what it can discharge, what it can get rid of, what it can relieve, hence the name relief valve, is it has to meet or ideally exceed the heating capacity of that heat source, a boiler typically, a heat exchanger, a water heater. So I got to meet the pressure rating says, hey, I can't, it's an older style sectional cast iron boiler. I can't operate higher than 30 pounds. That's what I'm tested for. So I'm going to have a 30-pound relief valve. But the other part of the equation is, hey, I'm a 50,000 BTU boiler. I'm a 5 million BTU boiler. Which one am I? I'm going to have two different relief valves. So when the relief valves are selected, and typically the appliance manufacturer a lot of times provide it. Sometimes it needs to be purchased separately. But these are two important criteria. What's the pressure rating? And then what's the heating capacity, the DOE? Those are two important numbers. So when you look at like a spec sheet of a particular pressure reducing manufacturer, they're going to have a pressure rating on that far left-hand column. So 30, 36, 45, 50, 75, et cetera. But then here, what are the BTUs? What's the capacity in BTUs per hour that relief valve can relieve? So make sure those two are compatible with the appliance you're specifying or attaching it to. How you guys doing? Throwing a lot at you real quick. Doing a lot of talking here. How are we doing, Willie? Is all set for maybe a quick? Yeah. Everyone that's online, we're going to stop. It's 5:30. We're going to get back together at 5:45 at the latest, 5:45. So I'm going to just stop the presentation, grab a quick bite to eat, a glass of water or whatever. We'll get back together at 5:45. Thank you. Well, we're going to get back together here and get going. Let's see here. Okay. So it's a little after 6:47. So we're going to get going. Next subject we're coming up, or that is coming up, is getting into pumps, pump curves, and then the system curve, and kind of that relationship that exists with pump curves and system curves. So without any further ado, we'll kind of jump right into it. I'll try to. This control will let me. So developing a pump curve. The various components that we just talked about, obviously the first one was the pumps, the centrifugal pumps, all different styles. But a pump curve, I mean, technically a purist would say this isn't a pump curve. There's no model number, there's no horsepower, there's no impeller diameter, there's no numbers, flow, feet of head, all the details that you typically see. It has the workings or the beginnings of a pump curve, but it is not a pump curve, technically. But what you can take away from it is on the bottom, horizontal here, moving from the left to right, this axis here will always list our capacity and flow. And typically what we're going to be referencing would be gallons per minute, GPM. And then this axis here, the vertical on the left-hand side would be feet of head, typically, PSI or feet of head. So it's kind of an expression of how much energy, how much foot-pounds of work per pound of water that passes through the impeller, through that volute that we just talked about, that energy that motor's spinning and the impeller's imparting velocity, how much energy, how much work have we applied? And we'll get in better details with that, but that's the pump curve, flow versus head. So at the very beginning, how do you determine the flow rate? And there's a couple of different ways and all of that, different formulas. We'll talk a little bit briefly about it. If we have time, like I said, we might get into that last device, that tool, that system Syzer calculator. But what they're trying to show here in this very basic drawing is, I have flow going through a pipe or a system. What is the flow rate and what influences? What are my, what can help me determine what the flow rate needs to be? So in this case here, they're talking about a change in temperature. It's a sensible temperature that we're measuring. So it's water. It's not a gas. It's not a steam. It's water. It's going to stay water. It's just going to change in temperature. Specific heat of the fluid, typically what we're dealing with for the most part is going to be water. There are instances and examples where maybe we're not, and that specific heat may change, which can influence the formula, the calculation. And then the last part here is, okay, what's the load? Are we trying to heat something or are we trying to cool something? Are we removing heat or are we providing heat? What's the BTU load? So a little quick drawing, if you will, or a sample saying, hey, I got a coil and I have a supply temperature, the red, hot, and then obviously as it's moving through this coil and there's a fan moving air across it and it's losing temperature, it's transferring that heat from the water to the air, I'm taking a temperature drop. And in this case here, they're saying, okay, my delta T, it's pretty straightforward, but what am I coming into the coil at? What temp? And what am I leaving the coil at? What temp? That difference is my delta T. A fairly standard number, which we'll reference as we move forward and that you'll hear throughout this and typically a lot of times in the industry, is a 20-degree delta T for heating loads. Supply it at 180, comes out at 160. Goes in at 200, comes out at 180. Not written in stone, doesn't have to be, but it's a very safe, very standard number for heating. So how much heat is the water carrying? And now we're getting into kind of building that equation, if you will, BTUs per hour. So we have pounds per hour over 1 BTU per pound over Fahrenheit. They're just talking about that's, what we need to do is we have this mass of water, this weight of water. We're going to define it. We're going to call it so that we can establish a flow rate of gallons per minute. So when you start plugging in this whole formula and then numbers start to cancel each other out, if you will, at the end, you end up with this kind of a standard formula that's used in the hydronics industry. And it's saying 500 times gallons per minute times delta T will provide the BTUs per hour that we're chasing, that we want, that we need. And so if you start plugging in these numbers and we stay with that example that we had the 20-degree drop between the inlet temperature to the coil and the outlet temperature, and we plug it in, going the wrong way here, we can say BTUs per hour equals 10,000 times the flow rate. And in this case, we're trying to establish the flow rate. So we just kind of reorient the equation and we say BTUs per hour divided by 10,000 will get me my GPM, my flow rate, my gallons per minute, my load. So BTUs per hour. Now the 500, where is that? Where's it coming from? Quite simply, 8.33 or 8.34 pounds per gallon times 60 minutes in an hour, because we're talking BTUs per hour, but our flow rate is measured in gallons per minute. So I take that 8.34 times my 60 minutes, there's my 500, In this case here, when I apply that number, I say 500 times my delta T, my change in temperature, 20 degrees, 10,000. That becomes my factor. BTUs, a million BTUs. What's the flow rate? 20-degree drop? 1 million BTUs divided by 10,000 is 100. 50,000 BTU load divided by 10,000 is 5 gallons a minute. 600,000 BTU snow melt application designed on a 20-degree drop, 60 gallons a minute. So it's an easy number. It's a very easy number to work with. But just know where it's coming from with some of that formula behind the scenes. Like I said, 20 degrees is very standard, but it's not written in stone. You can design on different delta T's. And as you do, that 10,000 becomes a different number as you just plug in 25 times 500 or 30 times 500. And that will influence, that'll change, because there's an inverse relationship between flow rate and delta T relative to load, BTUs per hour. The higher the delta T, the lower the required flow rate. The tighter the delta T, the tighter the delta T, the higher the flow rate. So it's just in the math. It's just a number, but just get comfortable with it. Any stretching? Now you have a question. Flow rate? That's a great question. The question asked in the classroom was, why wouldn't we just pick like the highest possible delta T, which would result in the lowest required flow rate, which is it is a design consideration. One of the concerns would be, and I'm just going to give you an example and we'll work through it. Because if I send it out, say I sent out water temperature at 180 and I allowed an 80-degree delta T. So now I'm coming back at 100. My terminal units that are out there now need to be configured for a much lower average water temperature. So I can take it to the extreme, and depending upon what I'm feeding, a terminal unit, a fan coil, radiation, baseboard, whatever the case may be, radiant floors, makeup air coil. If that temperature drop gets very excessive, just the heat transfer, the BTU output at that lower temperature could have a negative impact. If I can account for that by having this like oversized heat exchanger, heating surface area for the lower water temperature, I can do that. But a lot of times the amount of surface area that you would need offsets the benefit of using the smaller pump, the smaller diameter pipe, because the flow rate's lower. I'm compensating with other, so it's kind of like a trade-off. Design it on a 5-degree, that's crazy. The flow rate's so high, the pipes are going to be big, and I design it too wide, and now my radiation has to increase and change. So kind of a happy medium, if you will, or economies of scale, 20, 30 degrees. When we get into primary, secondary, and we start talking different flow rates mixing, that example, when you start playing with high delta T's, absolutely is a factor in a positive way, and it will work, and we'll get to that in a couple of weeks, I think. Your plant is right. Yeah, there are benefits to get to that lower temp. Just be aware, how the overall. I have it. We can get into that because we use that with like outdoor reset and stuff like that, and what has an impact and flow relative to heat surface area and temperature difference. That's a good question because you're seeing the value of reduce the flow, reduce the pipe size, reduce the pump. It's just, where's that trade-off? It doesn't shock the boiler. Yeah, a question came, if you get the water temperature too low, what does it do to the boiler plant? Depends on the boiler. If I have say a stainless steel high efficiency modulating condensing boiler, bring it on. I love it. You got a sectional cast iron boiler like a hot plate. I don't want to run ice cold water under it or over it. I'm going to thermally stress it and eventually shock it and damage that plant. So talking flow rate, the second part of that pump curve was pump head, or that foot pounds of energy. So what is pump head? So there's just a couple of terms that you kind of come across. Pressure, force applied against a unit of area. Fluid head, mechanical energy contained. Pump head, the energy or the work added by the pump as the fluid passes through the volute. So in a hydronic system, the liquid flowing, three factors influence the mechanical energy head and how it's transformed. So you got a force of static pressure, a head due to elevation change in an open system, and then the head due to the velocity of the liquid, velocity which would be what the pump has added through centrifugal force. So it's kind of an interesting screenshot here or drawing here, but what it's showing here is a pump operating in an open loop system. And they'll use the expression dead head up at the top here. So what they're saying here is based on the height of this open pipe, I have this circulator or pump, its suction is flooded, and it's pulling from this basin or this container of water. And what it's saying here is the water column or the elevation head equals the pump head, which is a 3 psi differential, or 3 times that 2.31, which equals 6.9 feet ahead. So in this weird, unusual scenario, I could turn the pump on and the pump's running. It's developing 6.9 feet ahead and no water's flowing. So there's no flow. I'm just maxing out my differential, which in this case is 6.9 feet, which happens to be, just the height of this open pump, or this open piping, I should say. Pump running, no flow occurs. Kind of an unusual, where I might have an open, and then where I take into account, say, that elevation, that static would be like a cooling tower, where I have a pump at the base, with below the basin. So there might be an actual positive suction head here, but now I got to lift that water, if you will, open up to the high point here to my spray nozzles or my fan. So what is my vertical height minus my basin height? So when I account for that pump selection and I have some piping flow rate, frictional resistance I got to design and account for, I also have this vertical height that I have to always account for to get that water to that high point. Moving to the next drawing here, which they'd refer to as a closed loop, which is going to be, I would imagine, a very high percentage of the systems you're going to be designing and working on currently and in the future, a closed loop system, where we're really just concerned with friction loss. So they'll make a statement over here, pressure, velocity, elevation are all equalized at all points. So I'm really concerned with calculating the friction head loss, which will then become my pump head. So I go back to that pump curve and I'm established a certain flow rate based on BTU load, delta T, what's my temperature drop? There's my GPM. Now, as I move this GPM through this closed loop, it's obviously a very, very simple drawing, but that could be a building, it could be makeup air coil, it could be whatever we want it to be. I've got to calculate just the frictional resistance, which will then establish my required pump head. Then I can go select a circulator to meet those conditions. Real quickly, it's just a kind of an explanation or a definition, but what it's getting, or what it's trying to show here is if I had a 1 pound weight, if you will, over 1 square foot area, and I kind of work the math, to display that in a gauge would be quite challenging. It'd be a 0.007 pounds per square inch. If I measure it 1 pound across 1 square inch, that's where I can now start use gauge readings, and I can start saying, hey, 1 pound per square inch area. And that's what a gauge reading is, PSI, pounds per square inch. So where that comes into play, obviously referencing a pressure gauge, but where it can come into play, you start, I guess, again, a little bit of terms and units of measurement, but you got absolute pressure, you got atmospheric pressure, you've got gauge pressure, and then you have vacuum pressure. So what they're just trying to show here in these different scenarios, if you will, is atmospheric pressure 14.7 if we're at sea level, and I think they mentioned that. Assuming elevation at sea level here, 14.7 psi, right? Which would reference on a gauge 0 psi G, 0 pounds per square inch gauge. If I had an additional, system attached where I filled it to 4 pounds, then I would have a gauge reading of 4 psi. If I was trying to read that combined atmospheric and my 4 pounds gauge in absolute measurement, it would read 18.7 psia. But the gauges are typically, when you're reading the gauge, it's just going to be pounds per square inch gauge. It doesn't add in absolute. Then you can get into vacuum, which typically we're not dealing with sometimes from a problem standpoint, where we create a vacuum and we put water or the system into sub-atmospheric or vacuum. That can create some problems. But really, it's just to be aware of gauges are reading everything. 0 pounds gauge would be 14.7 psi absolute. And then anything above that is now going to be reflected on my pressure gauge. So static pressure, pressure caused by the weight of a column of water. Rule of thumb for water, 60 degrees. It can change, but the differences as you get colder or hotter aren't hugely different. We'll go through an example in a bit. But a column of 2.31 feet of water is equal to 1 pound per square inch. So now he's saying, hey, just real quickly, I got this system, it's filled with water. I got a gauge at the base. What is that gauge going to read? What's it going to display? So I'm in a mechanical room, I'm looking at this gauge, and it says a number. What does it mean? Well, in this case here, what it's saying is, okay, what's the physical height in feet? What's that height? Divided by a 2.31. And then in this case, if you have positive pressure at that high point, that would be represented by P2. Add those two together, and that's what that gauge P1 would be displaying. So the physical height divided by 2.31 plus any positive pressure at that high point, that's what P1 should be reflecting, should display. As an example, which typically, I don't know how often this would ever happen, but halfway through a building in a height standpoint, they'll say, hey, I got a gauge here. It's represented as P3. What is that displaying? Well, again, it would just be the height from where that gauge resides to the highest point. Again, in this case, H2 divided by 2.31 plus, again, that positive pressure, and that's what gauge 3. So when you're looking at gauges, and that happens out in the field, sitting in your office or whatever and designing, not that often, but you get out in the field, gauges are referenced a lot to find out what's going on in that system. Is it filled? What's the pump doing? What's the pressure differential? All of that. Just recognize what you're reading and what it means, what it's displaying, what type of information is it giving us. Just real quickly, where does the 2.331 come from? So it's just saying, hey, a 1 cubic foot of water at 60 degrees weighs 62.4 pounds. 1 square foot of area has 144 square inches. It's just doing math. It's playing a game back and forth. 144 divided by 62.4 is 2.31 feet per square inch, pounds per square inch. If you did it the opposite and said, hey, take my pounds, divide it by my 144 square inches, it's 0.43 pounds per foot. So I can go back and forth. I can convert from PSI to feet ahead or feet ahead back to PSI. That's all it's reflecting. And a pretty standard number would say, hey, at 1 pound of water at 60 degrees Fahrenheit, if I had it in a tube and it was 2.31 feet in height, and I had my pressure gauge at the base, it would read 1 pound per square inch. And what they're trying to show, just to reflect that dimension or that measurement, square inch, they say, hey, I got a tube that's 1 square inch. But anyway, so it's just information. You kind of get into the weeds. It'd be good to reference it later on, in the slide deck that you'll have access to. Kind of an interesting slide. Some people, can appreciate what they're trying to show here, but they're saying as water's moving through that closed loop system and it has this energy that's been added to the water as it passed through the pump, if you have gauges throughout the system, those gauges are going to reflect a drop in pressure. That drop in pressure is just evidence that there's been work done. There's been energy consumed to move the water through, in this case, the piping system, this frictional resistance. How much? Well, we calculate that. We figure it out. And then we pick a pump that can move the flow rate based on the BTUs and overcome the frictional resistance of that closed loop system. So now you're kind of jumping right in. We're saying, okay, I got this system. It's pumping 3 gallons a minute through a coil, a hydronic coil, chilled water, whatever the case may be. And I have gauges on the inlet and the outlet, and they're reflecting a 5-pound pressure drop. It's coming in at 40 and it's exiting that particular coil or whatever 5 pounds lower at 35 PSI at a flow rate of 3 gallons a minute. There is this inherent relationship between the change in flow and the corresponding change in pressure drop based on this calculation that we're going to kind of jump into right now. There's a relationship. When you have a known flow rate and a known pressure drop, when you change that flow rate in that given system based on the original flow, which means you calculated the original pressure drop, in this example here, 3 gallons a minute at a 5-pound pressure drop. If I want to change that flow through that same coil, I know what the new pressure drop is going to be. It's going to be the less if I reduce the flow, it's going to be more if I increase the flow. And a lot of times in the industry would say, hey, if you double the flow, you're going to double the pressure drop. It's a direct relationship. And if you look at that formula, it's not. And what they're trying to show here is a change in flow, whatever that relationship is, square that answer, times it by your original design head. So the change in flow, the resulting pressure drop is a squared relationship. So I double the flow in this case. And I say, hey, 40 PSI coming in. I've increased my flow rate to 6. What's the pressure drop? Well, my known flow was 3. My new flow is 6. 6 divided by 3 is 2. 2 squared is 4. 4 times my original 5-pound pressure drop. I'm going to experience a 20-pound pressure drop through that same coil if I try to double the flow rate. Something to be aware of. I got an existing system and I want to increase the flow. Recognize as I try to do that, there's a squared relationship of that increase in pressure drop. I want to be aware of that. That's the beginning of just starting to understand pump curves and system curves, the relationship that exists. So when I change the flow, whatever that difference is, I square that number times my original design head loss. That will give me the answer to my new pressure drop. Conversely, go the other way. 3 gallons a minute, cut it to 1.5. The pressure drop's not dropped down from 5 to 2.5. It goes to 1.25. So now you start getting into variable speed pumping and energy requirements and horsepower and kW savings as you get into big systems. So pressure drop, friction loss, and flow rate relationship. There is a relationship. So the system curve, and the system curve is based on that formula, if you will, that I have a design flow rate and a design head loss. I want to increase or decrease that new flow. Square that answer times my original becomes my new head loss. And so they're going through this exercise, and it's just building a system curve. And they say, hey, I've got a design condition of 200 gallons a minute and a corresponding pressure drop of 30 feet. If I want to build a system curve, what I can do is arbitrarily pick either other pressure drops, figure out the new flow rate, or arbitrarily pick other flow rates and establish the new pressure drop. But at the end of the day, either way, what we're just showing here on that system calculator, scale 5 can kind of do that for us. And then there's actually electronic versions of the system Syzer for your laptop or your PC that you can plug in on your computer. And it's a real quick, calculation, but all of it is based on this formula back here. Q2 over Q1 squared times your H1 will give you establish your H2. So I have a design condition, 200 gallons a minute at 30 feet ahead. I can arbitrarily pick these other numbers and I will plot them and create what was called a system curve. And that system curve is establishing, showing that relationship. If I know 200 at 30 is accurate, I've calculated the flow and I've established the pressure drop. Any other flow, I can calculate the corresponding new pressure drop and I can create the system curve. And the reason for that is this. The system curve is always going to intersect the pump curve. And the ideal setting is to buy, select, put in a pump that meets your design criteria. A lot of times that doesn't happen exactly, and you can calculate, okay, or the software nowadays will calculate where is that pump actually operating. But there's this relationship, this squared relationship. It's kind of maybe a little confusing at first, but all it's saying is once I know a given set of conditions, in this case 200 GPM, 30 feet ahead, I know what that system curve is going to look like. And the software nowadays, years ago, the old, years and years ago, they would sit down and mathematically do what we just talked about. Today, you plug it in a software, spits it right out, tells you exactly what the curve is, where it's going to intersect. Yes, sir. Sure. Impeller trimming. Yep. The question coming from the class here was sometimes maybe your design selection and then what happens out in the field isn't accurate. One of the solutions might be to trim the impeller, make it smaller, more in line with what actually is happening in the system. And yes, that does happen. Variable speed drives kind of take care of that as well. They'll just, instead of running at full capacity, they might knock that hertz down from 60 to 50 to 44 or whatever the number is. But we have a lathe downstairs here at FIA and we trim impellers. Sometimes it's to build the pump from the beginning. Other times, not as common. They might be out in the field with the problem. They'll take the pump impeller off, bring it here, and we'll trim it, put it back on that pump. But it will have the same impact. You'll change the speed, you'll change the diameter, you'll change the capacity. A quick example here of an open loop cooling tower. And when the reason for this would say, hey, if I'm going to develop a system curve, the whole thing isn't variable. That friction loss isn't variable. There is a fixed static head. There's a constant. And that's the way they refer to it. Account for the constant head loss. Well, that's that vertical lift. As I change this flow rate, that 10 feet doesn't go away. I still got to always account for that height, that static. So if I was to build a system curve for that set of conditions in this open system, I'm not going from 0. I'm starting at, I have a built-in constant 10 foot of pressure differential that pump has to develop to overcome that vertical lift to get that water to that high point for that cooling tower. The variable will be, okay, as I change the flow, okay, yeah, the pressure drop in the piping, through the condenser, through the piping, that will change. That's variable. Given the pipe size doesn't change, it's given. As you reduce the flow, you reduce the pressure drop, increase. But that 10 feet never goes away. So when I build that curve, I always have that constant. Fluid head loss in a pipe. How much over a given distance? Rate of head loss. It's kind of an industry standard, but they'll say it's measured in 100 feet. So what's your pressure drop in feet per 100 feet of pipe? When we look at this system, Syzer, we'll look at it later on tonight or maybe tomorrow, excuse me, next week. And if you look at pipe sizing charts, they typically will always reference feet per 100 feet of pipe, or TEL, total equivalent length. So as a quick example, they'll say, hey, I got a 2-inch copper pipe. I have a flow rate of 30 gallons a minute. When I look it up in software, whatever tool I'm using, that's going to experience a pressure drop, a friction loss rate of 2 feet per 100 feet of pipe, of equivalent straight pipe as it travels. So 30 gallons a minute, I got 500 feet of piping, TEL, 500 feet. That's telling me I would need a pump that can develop 10 feet of pressure differential so that I can move that 30 GPM 500 feet worth of piping. Because for 100 feet, it's going to experience this 2 feet. So 500 feet, just 5 times 2, I need 10 feet of head for that pump curve, for that pump to develop to overcome the friction resistance. As a rule of thumb, and as soon as you make rules of thumb, things can change. But when selecting pipe sizes, friction loss, typically, you don't want to be greater than around 4 to 5 per 100 feet, especially in closed loop, heating and cooling in dormitories, office spaces, hospitals, places where noise can be a consideration. When you're in commercial manufacturing, maybe even pharmaceutical, maybe that 4 to 5 feet can be expanded. These are some charts. This is out of an ASHRAE book, a 2021 fundamentals book, and it talks about different diameter pipes. They have it in categories. How many hours out of the year is that pump running? The longer it runs, the lower the flow rate that they want to select for energy consumption. They're a little more liberal on the lesser hours per year. But again, it's all referencing, what's that pressure drop? And you'll see it, feet per 100 feet, feet per 100 feet, etc. So it's just kind of an industry standard. When you calculate that pressure drop, that answer you come up with is usually feet per 100 feet. And then you're just going to say, okay, how many feet do I have? 1,000 feet or whatever the number is. One other thing to be aware of, which again, software a lot of times takes care of it, is fittings. Fittings offer a certain pipe equivalent length, a TEL they'll call it. So as a quick example here, they're saying, hey, if I was just to highlight a 2-inch T with a side branch in or out, I'm saying that a 2-inch T has the equivalent length of 5 feet of piping. So 1 T would be like having 5 feet of pipe. So as you're designing this pressure drop and you're designing the system, well, yeah, there's going to be a tremendous amount of straight run of pipe. But there's also going to be fittings, T's, elbows, etc. That needs to be accounted for. And at the end, you'll establish this TEL, total equivalent length. And that's what you're going to say, okay, my copper pipe, 30 gallons a minute, 2 feet per 100. What's my TEL to establish my total required pump head? And then, once you get past that, what else is in that system? Is there a boiler? Is there a fan coil? Is there a control valve? Is there a balance valve? So they have what they call these KPDs. It's just known pressure drops. So a lot of manufacturers will have literature that help us. It's all online nowadays. But it will say, hey, I got this zone valve, just for argument's sake, a control valve, a zone valve. I have a performance chart that says, hey, depending upon the flow rate, I know what the pressure drop's going to be. I have this baseboard. Well, I have this literature from the manufacturer that tells me the pressure drop. I have a balancing valve. I have a performance chart that's going to say, hey, what's the, so I have all of these pieces of literature that list out the various pressure drops for the control valve, the terminal unit, the balance, the flow control, or the check valve. You got to account for that. So in addition to the piping, which is very important, now what else am I putting it through? And the manufacturer, these manufacturers will list or have these known pressure drops listed, rated. Kind of an interesting drawing, and it's saying a series piping versus a parallel. And this sometimes trips people up. In this orientation, whatever the flow requirements, the BTU load is, everything, terminal units and piping are all in series. So when you're establishing the pump head, you're accounting for everything that's in line because it's one loop. This is not that common in like a fan coil application because you're going to be more in this orientation over here on the right, the parallel. But if I had like in this room right here, I have baseboard. And then I go to the next room, I have more baseboard. It's in series. So I would be calculating not only the pipe diameter, but the pipe diameter of these terminal units. And I'd add it all up to establish a known pressure drop. Over here, now I'm in parallel. This is different. As this pump is pumping the total desired needed flow rate, I don't have to add up the pressure drop of every branch here. Why? Because as long as I calculate the pressure drop of the branch with the greatest pressure drop, then I have enough pressure differential head capacity from the pump to overcome the lesser pressure drop loops. So all things being equal, this radiation is all the same, the required flow rates are the same. This just happens to have the longest run, so the most amount of piping associated with it. So I'd want to calculate that to establish my required pressure drop. But I wouldn't have to add in the pressure drop of D and C and B in addition to the pressure drop of A. I just have the pressure drop of that circuit that feeds A, but the total flow rate of D, of D, C, B, and A. So the pump has to move all that flow because all four zones could be calling, but I only have to overcome the pressure drop of the guy with the greatest resistance. Don't add them all up because then you start adding, you're overheading. You're having a pump that's way too big. And then when you put that pump on and he doesn't know he's too big, he's just shoving way too much water throughout your whole system. You're oversized, overpumping. You don't want to do that. And this is just a quick other example of that. Saying, hey, I got 4 circuits. I have a boiler. I have air separation. I have gauges. I have control valves or zone valves. I just want to calculate the TEL times the friction loss, right? What's the measured length plus the equivalent length of fittings? I want to figure this. What's my longest run, right? What's my longest run? And what's my component pressure drop of the longest run? So for the critical circuit they're referring to, in this case, again, all things being equal, I want to calculate the pressure drop of this guy. This is the furthest run. It's got the most amount of piping. It's going to offer the most amount of resistance. You can have scenarios where that doesn't hold true. I have 3 fan coils that are all, say, got the same pressure drop, and a 4th one that, for whatever reason, is very small diameter, whatever it is, but it has extreme pressure drop. And it might not be the furthest one away. This becomes the boss then. I calculate that guy with the highest pressure drop. And if I have a pump head that can overcome that, then he can overcome the other 3 lesser pressure drop zones. So you just got to be aware. Pump curves, fundamentals. We kind of started talking about this. But any kind of flow and head must intersect the pump curve. When the pump turns on, it's going to operate somewhere on its curve. Where that pump curve and the system curve intersect, that's where, I guess you could say, it satisfies the law of conservation of energy. Energy in, energy out. The pump like he doesn't know what you selected. It's just going to turn on and it's going to run and it's going to pump as many gallons a minute as it can relative to what the resistances the system offers. We want those two ideally to intersect, that system curve, performance curve with the pump that we designed, specified, selected. That would be ideal. So when you look at a pump curve, how do you read it? What's that? There's a lot of information right here in this chart. It's actually quite busy and it can be confusing. So, but this is not uncommon. This is pretty standard, whether it's in the old catalogs or nowadays you guys would be online. You'd get online with software and say, hey, I'm looking at in this particular one and saying, hey, it's a series 1510. It's a base mounted end suction. This particular size, this 2.5 BB operating with the 1750 RPM motors. This is the footprint, or this is the DNA. This is the performance capabilities of this model. And it's not just one point, it's several different points. You've got these, the first thing that's going to highlight is going to say, instead of calling it a pump curve, we're going to call it an impeller or performance curve. It's very specific to the impeller you select. And you're going to select that impeller, or the computer software is going to select that impeller based on what are your design conditions? How many gallons a minute at what pressure drop at feet ahead? And so where it comes in, this comes into play is right at the very beginning tonight, we were looking at pumps, centrifugal pumps. We were looking at the cutaway of a pump, and we had the diameter of the impeller sitting inside the volute. Then we had this cut water. And we said, hey, that circulation discharges out. Well, where it comes into play is this particular size, this 2.5 BB, can support a full-size wheel, a 9.5-inch diameter impeller, and you can cut it, you can trim it all the way down to 7.25 inches, and anywhere in between, typically in 1/8-inch increments. But you don't want to go below that 7.25. And it's not that you could, but that wheel gets so small inside that volute that a very high percentage of the water that impeller is spinning recirculates, becomes very inefficient. So this pump curve says, hey, this is the range that you want to operate in terms of selection. If you have something greater or lesser, this isn't a pump for you. Go get a different size, bigger or smaller. So that's the first thing when you look at this pump curve is impeller diameter performance curves. Horsepower. What horsepower do I need depending upon the condition? The manufacturer tests it and says, hey, depending upon where you are in these curves and performance, these are the size horsepowers you need to select to perform the performance you're looking for. These are what they call the BEP, best efficiency points. So where do you want to pick a pump? And ideally, maybe close to that BEP, but there are standards. You can be a little bit left of that, or you can be a little bit right of that efficiency BEP point. And as you increase or decrease the impeller diameter, you move closer or further away from those efficiency curves. Down here on the bottom right, they have this thing sits off to the right and it says NPSHR. Down here on the right, and what it's saying here, and this is the curve, net positive suction head required. This is established by the pump manufacturer. He says, I need to have this much static positive pressure of water in the pump so that I don't cavitate. So there's two NPSH numbers. One's called R, it's established by the pump manufacturer. He knows his design. And then the next one is A, what's available? What does the system provide me? We'll get into this a little deeper later on. But that's just from an information standpoint, when you look at this pump curve, you got diameters, you got horsepower, you got efficiencies. Off to the right, you have this NPSH required. This is the manufacturer saying, make sure you give me this type of net positive suction so that I don't cavitate, I don't damage the pump. And then the last one has to do with these efficiency ratings that the DOE started to establish or ask the pump manufacturers to establish these ratings. was it back, what does it say, Will? Back in about 4 years ago, some of the pump manufacturers started applying the PEI, right? Pump efficiency information or whatever, ratings, index. There you go. So it's very busy, but it actually, you break it down, there's a reason for it. They all make sense. The preferred and the acceptable operating range. So the POR and the AOR operating ranges. And what's happening is they say, hey, I got this range, BEP is here, and I can move a little bit to the left of it or a little bit to the right of it, and I'm okay. But if I get extreme and I start moving past that percentage, I can really damage the pump. I'm going to be very unhappy. The building owner, whoever bought this pump, is not going to be happy with the performance or the life cycle, the frequency of service, bearings, seals, etc. So best practice and good practice, so like preferred versus acceptable. But you typically don't want to go past either the best or, at the worst case, the good practice. And again, you know, there's all these different ratings that come from the Hydraulics Institute. We're dealing with speed, so less than 4,500 RPMs. That's our world. 36 to 1,800, 1,200 RPMs. So typically, we don't want to exceed 70% of, all the way up to 120% of. So 20% greater, 30% less of that BEP. Now, what is it? We were looking at right here. So in this particular pump, this is the BEP. So if I go 30% to the left, 20% to the right, I'm within hydraulic, ASHRAE, all these other governing bodies. That's okay. Pump manufacturers say, yeah, the pump's going to operate. It's not going to create problems. You start drifting outside that, you're going to have some issues with the life and the performance of that pump that you've specified. Just real quickly, getting into horsepower. There's two different. There's a work horsepower, or excuse me, a water horsepower and a brake horsepower. And all it's saying here is the water horsepower is your flow times head times specific gravity divided by 3960. I'll explain that in a second. By the pump to provide the water horsepower. The brake horsepower is that's what you're paying your electric bill, because there's an efficiency loss. So you're using a little more horsepower required because of some of the efficiency losses. So 3960, all it is divide the number of foot-pounds for 1 horsepower, 33,000 foot-pounds, by the weight of a gallon of water. It's that's that factor, that 3960. What's the efficiency of that pump? You do the math, you do the calculation, that becomes your brake horsepower. Quick picture just saying, hey, this is the picture of a pump, the wet end. I have my impeller, I have my shaft, I have my seal, I have my volute. Here's my bearing assembly and my coupler behind it. What are my losses? Bearing friction, mechanical seal. There's rubbing as it's rotating at 1800. There's some frictional loss. There's fluid friction inside the volute. There's a little bit of that recirculation. As that impeller's adding that velocity and that water's churning in that volute, a high percentage of it discharges out, but a little bit recircs. All of those add up to, and this is a deep dive into the engineering of how a pump is built, just behind the scenes. You're not going to spend all your time, but go back real quickly to that pump curve. Okay, I got a chilled water application. I got to feed 50 fan coils. What's my load? What's my pressure drop? This is the information you're going to see on that pump curve to make the right decisions. And again, motor speeds, 1200, high flow, low head. So a lot of flow rate, gallons per minute, very low pressure drop, maybe low NPSH, or more commonly, it might be a cooling tower. Might be an application you guys are going to bump up against. 1800, absolutely the most common that we're going to see in a closed loop heating and cooling application. And then 3600 RPM, very low flow, but very high head. Process is a very common application, perhaps. with the higher RPMs, maintenance intervals, et cetera, bearings, higher speed, higher temperature. A couple of different enclosure types, ODP, TEFC, totally enclosed, fan cooled, air over, not that common, and then explosion proof. On the different types of enclosures for the motor itself that you're going to see out in the field. Duty point or non-overloading. When you go to select a pump, you have two sets of conditions. Do I want to pick it to duty point? What is my design condition? Or do I want to pick it to non-overloading? So as you say we get into some software and I'm picking a set of, I'm trying to select pumps and I'm typing in, I say, hey, what's my flow rate? I need 475 gallons a minute. Through my calculations, I've established I need 65 feet of pressure differential, a feet of head. Motor sizing, motor settings. Select it based on duty point. Duty point means that flow at that feet of head. That's my very specific condition that I've calculated. So pick the pump accordingly. And when I do, here it is, here's the exploded pump curve with the system curve. I've got a control head here, so my system curve doesn't start down at 0, it starts at 20 feet. But what it's talking about here is at duty point, I'm not moving past that flow rate of 475 at 65 feet ahead. And when I look at the required motor, the horsepower, it says 10 horsepower would be adequate. That'd be the proper horsepower at duty point. The next option would be, hey, I want to pick it at a non-overloading selection. And where this comes into play, all of a sudden, look at this motor horsepower that you've picked. It went from 10, which is adequate, 475 at 65. It says, hey, let's be safe. Let's pick a non-overloading motor. I'm going to bump it up to 15. And here's the reason why. At that duty point, this is the impeller that I need, 8.75 inches. If I follow this curve and I start to move past that duty point, I quickly can pass that 10 horsepower, which is these dash marks right here. If I start to drift past that, I can overload that motor, I can overheat it, and I can shut it down. So then you say, well, why would I ever do that? Well, in reality, like if I'm doing a process and I'm taking water from a vat, going to whatever that is, and back, and that's it, it never changes, I could probably do duty point and be perfectly fine and safe. But if I'm taking this 475 gallons a minute and I'm feeding a whole bunch of fan coils that are distributed through a piping network, and they get control valves, and they're opening and closing, and I'm relying on a balance contractor to go in and balance this thing perfectly fine, and it may or may not happen, it's a very strong possibility that that pump may be drifting left or right of that duty point. And if it drifts out, and the reason it might drift out is this, I might not have 65 feet of pressure drop in that system. It might be something a little bit less than that to get that desired flow rate. So if I'm 60 feet ahead, and all I'm looking for is that 475, but I'm staying on this curve, I might drift out past that 10 horsepower. So to protect as a good selection, I'll probably type in my software, say, hey, right up here in the motors, pick non-overloading as an option. And now I've protected myself. Regardless of operation of that system, I'm not going to overload because that curve, that impeller performance curve, never goes past, never gets close to that 15 hus. It's a safe selection. It's always going to be fine. It's never going to overload in this example. So when you hear that expression, duty point or non-overloading, that's what it's all about. You just make that decision when you're plugging in your software. How do I want the motor selection to be? Right to the performance point or non-overloading? This is just getting into specific gravity and how it can influence the amount measured in pounds per foot. We don't need to spend a lot of time other than knowing that there's different properties, water, which we're typically going to be dealing with, but you could get into some type of process where you might have, some other, maybe it's a oil or a gas or whatever the case you're in, some type of mill or processing, it will influence the pump curve, the feet of head. Another look at static pressure, just saying, look at, if I got 60-degree water, I got 100 feet, do the math, it's 43 PSI. That's what the gauge would read down at the very bottom of that 100-foot column. If I had 230-degree water and I was reading 43 PSI, it would technically be 104.5 feet because my specific gravity at 230 is slightly different than at 60 degrees, a little lighter. If I had ethylene glycol, 40% mixture, that specific gravity is a little different, a little heavier. So now at 43 PSI, I'm only developing 92.8 feet of head. So specific gravity can influence. Where that comes into play, let's just kind of finish with this last example here. What it's showing here is if I had a pump out in the field, and it's answering this question, why when I look at these pump curves am I using feet of head instead of PSI on the pump curve? Everything's listed in GPM on the bottom and feet of head on the horizontal left, or vertical left, I should say. So pump delivering 30 feet of head. I'm dealing with 60-degree water. I'm developing a differential of 12.9 PSI. With 62.34 pounds, we talked about that 60-degree water, 30 feet times 0.43 PSI is 12.9 PSI. So if I was to look at the suction of the pump, the gauge on the suction, and it had 80, and when it turned on and it developed 12.9 PSI, I know that 12.9 PSI with 60-degree water is 30 feet ahead. When I suddenly am pumping 300-degree water, which is not the norm, but you might have an application where you're pumping 300-degree water. Well, I know the specific gravity of 300-degree water is different than, or the weight, the density is different than at 60 degrees. And in this case here, it's 57.31. So when I divide that by the 144 square inches per pound, I have a number of not 0.43, but 0.4. So when I have that 30 feet times 0.4, I'm going to read a 12-pound differential across the gauge. Still moving 30 feet of head, developing 30 feet ahead, but it's going to read differently on the gauges because the weight of that water is different because I'm dealing with 300 degree. The density is different than at 60 degrees. So the pump manufacturer doesn't have to make different pump curves for different water temperatures. It says X number of gallons a minute, 30 feet ahead. That's what I'm reading. What the gauges are going to show, they're going to be different. If I'm out there with gauges trying to say, what's the pump doing? If I'm dealing with 300-degree water, I'm not going to read 12.9. I'm going to read 12 if I have that 30 feet of pressure differential, which is what I calculated I needed. I think we've come to the end of the first week. Based on the looks of what I'm seeing here in the classroom, not sure about you guys back home or where you are in your offices, but I think we've met our limit. So I just want to say thank you very much for the first week. We will reconvene next Thursday, same time, and we'll log in like we did tonight for our virtual attendees. And then people in person will be here, and we'll start with week 2. So I just want to say thank you. Everybody have a good week, both here in the classroom and everyone remote virtual. So thank you very much.
Thank you. Have a good night.